Okay, so today we're very fortunate to have Johan Commelin, who will tell us about lessons from the Liquid Tensor Experiment and I suppose what it means to break the one-mind barrier. So thanks, Johan. Please take it away.
Yeah, thanks a lot for the invitation. It's a pleasure to speak for you guys. So, right, I'll try to explain what I mean by the title. But first, let me say a little bit about the backstory. And it all started, well, almost 2 years ago on the 5th of December. And you should know that I'm Dutch, and in the Netherlands, the 5th of December is a bit of a holiday. It's called Sinterklaas, so sort of a version of Saint Nicholas, where everybody gives each other presents. And so on the 5th of December, Peter Scholze posted a challenge online on a weblog, and I regarded that as one of the presents I got that day. So the challenge was as follows: check the main theorem of liquid vector spaces on a computer. And so I'm not going to explain what liquid vector spaces are, but it's a brand new sort of mathematics that Scholze has been developing together with Dustin Clausen. And it's all about unifying approaches to functional analysis and algebra, and making algebraic methods available in analysis, unifying in particular also different kinds of geometry like algebraic geometry and analytic geometry and that kind of stuff. But I'll not go into that. I'll focus on like the second line, so checking something on a computer. And what does that even mean? So for decades, there has been software around that allows you, like in a sort of very specialized programming language, to enter definitions and theorems and proofs in this computer language. And then the computer will, as compiling this programming language, it will check whether the proofs are line by line correct and deduce whether the proof is actually a proof down that can be checked all the way down to the axioms of mathematics. So that was what the challenge was all about. And 9 days later, the following picture was posted to Twitter. So you might not know these guys, but these are 4 rock stars. They form a band called the Liquid Tensor Experiment. And well, if you don't know what a rock star is, think Fields medalist, but music. Anyway, so that didn't really answer the challenge posed by Scholze, but it was a wonderful coincidence. So here's the history. These guys released their first album in 1998, and 1 year later, they released a second album. And so by induction, you would know what happens in 2000, except there was radio silence for 20 years. And it took a Fields medalist to write a blog post to get these guys back in action again. And so 9 days after the blog post, they announced, okay, we'll do a third album. The album was released somewhere last year. And finally, summer this year, we actually formally verified the main theorem of liquid vector spaces, finishing the Liquid Tensor Experiment. So today I want to tell you about some lessons that we learned along the way. And I claim that formal mathematics is useful, or we found it very useful for large collaborations, for reducing the cognitive load that comes with understanding proofs and verifying that a proof is correct. It helped us with what we called spec-driven development, and I'll explain what that is. And it helped us with gaining confidence in the correctness of the results, and sort of getting peace of mind that the proof was correct, that the theorem worked, etc., and also other aspects that relate to that. So I'll expand on all of those. And I want to stress, just please ask questions at any time. I'd like this, like if questions pop up, I'd like to answer them right on the spot. Right, so first let's look at these large collaborations. And traditionally, maths is really dominated by smaller collaborations. So there are a lot of single author papers and maybe 2 or 3 author papers. But recently we've seen larger collaborations appearing. So there are like 10 author papers or these polymath projects that have been promoted by Gowers and I guess Tao. Yeah, and we also see that technology plays a role in this. So there's the archive, there are weblogs that are used for these polymath projects. I think Math Overflow is a wonderful piece of technology that sparks a lot of collaboration that in a way that wasn't possible some time ago. And yeah, so sort of these interactive theorem provers fit right in. So they make it very easy to scale to large collaborations. There was a project in Koch roughly a decade ago, a bit more, that formally verified the Veit-Thomson theorem, also known as the odd order theorem. And this team had about 15 contributors. A bit later, we had the formal proof of the Kepler conjecture, led by Tom Hales. This was called the FlySpec project and was carried out in Hull, Isabel, with roughly 20 contributors. And so the project I'll be talking about, the Liquid Tensor Experiment, which we did in Lean, a pretty new theorem prover developed by Leonardo de Maura at Microsoft. And we had roughly, well, it varied over time, but roughly 15 people have contributed to this project. And so we didn't just use Lean, although it was, of course, the main piece of technology that we used and the thing that bound everything together. But we also used a bit of blueprint software that was developed by someone in the Lean community specifically for these kinds of projects. So you write a document in LaTeX, and I'll show the results. So you write a document in LaTeX, and you add some extra macros that tell you which, like if you write down a lemma, you can link to definitions, which you usually don't do, but you link to all the definitions and all the lemmas that you need to prove before you can prove this lemma, for example. And you can also add hyperlinks to the corresponding Lean code. And then part of this software also generates a dependency graph because you now know exactly which definitions are needed to state a certain lemma or which lemmas it needs for the proof. And this dependency graph is very useful for larger projects to understand what depends on what and also to track progress. And finally, of course, Lean ensures that everything fits together once you start formalizing everything in Lean, and ensures the correctness and compatibility of all the various components. And the result of this is that contributors can just look at this dependency graph and find subprojects that suit them and see, okay, here all the dependencies have been put in place, so now I can start working on this lemma that I understand quite well. And at the same time, they don't need to understand the bigger picture. I mean, it's still very nice, and I think this dependency graph and Lean, etc., can also help with that, but you don't need to, because you have this assurance that everything fits together, and the software guarantees that there are no mistakes and everything is compatible.
Johan,
so,
quick question. Is this blueprint software kind of, are there plans to make that independent from Lean and independent of this project, to make it
so it's
independent software kind of
yeah
differentiated?
So here it is. It wasn't written for this project actually. So it was written by someone in the Lean community for another project on like the sphere version and things in like geometric topology and the Gromov-H principle, etc. And then we used it for this project as well. So at the moment, it's sort of tied to Lean, but I don't think in a very fundamental way. So it could easily be decoupled from Lean. And so as you can see, like we can just click around. Let's see, just to a random section. wait a second for all the LaTeX to render. And then you see that this looks like a pretty ordinary LaTeX document, although it's rendered on the web. And then if we go to some lemmas, say over here, then if you hover over it, you see that there is this little lean logo popping up. And if you click on that, then it gives you a link to the lean code. There can be multiple links. If sort of a lemma says, well, the following three things are true, then maybe in lean it's 3 different lemmas. And you could click on that, and then it jumps to GitHub, where all the source code is hosted. And you can try to see how this statement matches this statement. Okay, well, it's pretty technical. That's also the reason why Scholze wanted a verification. There are epsilons and deltas all over the place. So we'll not actually look at that comparison right now. But you can sort of see how these hyperlinks work. And then there are like, so here's the graph. And at the beginning of the project, this was all white, and gradually it became more and more green. And so finally, when this main theorem was done, which says that a certain X group in the category of condensed abelian groups vanishes for all I at least 1. Okay, so when that was done, we knew that, okay, Lean had certified that this entire proof was correct. And as you can see, okay, I need to move something out of the way. This graph is reasonably small, and you can sort of understand this structure in your head, but everything depends on this node at the left called first target. And so that's actually the entire content of the first section of this blueprint, which has a different graph attached to it. And okay, for some reason, my internet is a bit slow. Okay, and that's actually where the bulk of the work was hiding. So you can see that this graph builds up completely to this first target node. And so this is a pretty complicated graph, and it really helped us a lot to like track where things were happening and where we still needed more work, and also what kind of, like, it was pretty easy to see, okay, here we need some homological algebra, there we need some analysis, etc., etc.
What's the significance between ovals and boxes?
Lemmas versus definitions. So boxes are definitions and ovals are lemmas/theorems.
Yes.
Yeah. Okay. Right. And so here's a list of people that made major contributions to the project, and then many others also made smaller contributions. So it really was like, in all my traditional math projects, I worked with like 2, 3, maybe 4 people. And so this was quite exciting to have so many people with really different backgrounds, people specializing in homological algebra and higher category theory, and others that just have a background in something completely different, like analysis or some forms of topology or contact geometry or computer science, and everything came together. And that was really exciting. So the next item I want to talk about is this cognitive load. And maybe here it's the most clear that you can sort of break through a one-mind barrier. So, okay, so with the previous topic of like these large collaborations, you sort of break through a one-mind barrier because you don't have to understand everything on your own, and you're not just working on the entire project yourself or with maybe 1 or 2 extra minds, but now there's this huge expansion to 10, and I can easily see this scale to 50 or 100 people working on one project. So in a sort of horizontal sense, you break through a one-mind barrier. And here with this cognitive load, you break through the barrier in the sense that you can sort of expand your own mind. So regarding this cognitive load, I should say, when you're working on mathematics, there are differences, profound differences between finding or creating a proof versus checking/understanding a proof that someone else found. And well, this project was mostly about checking and understanding. So what I'll say also mostly applies to that, but some parts will also apply to the finding/creating of proofs. So I think, first of all, cognitive load arises from just raw proof complexity. If you have a very complex piece of mathematics, then it's just really complex. And unless you find a completely different angle of approaching it, there's not much that you can do about that. But cognitive load also arises from other things, such as keeping track of side conditions to lemmas, because, well, you have a lemma and it relies on two fundamental assumptions that are pretty clear, but maybe you also need to check one or two other conditions that are sort of annoying to keep track of and might not even be stated. But to be precise, you need to keep track of them. Another really weird thing that happens in mathematics a lot, which, well, it's also natural, but there are often very small discrepancies between statements and proofs. So you'll write down a statement, a nice and clean statement, and then you'll prove something. And then later on, you want to use the lemma, and you realize, well, actually, the proof was stronger and proved something extra. It proved more than just the statement. And so you have to mentally keep track of this because you want to apply it in a situation where you need it actually a little bit more. And this is fine because the proof proved a stronger statement. Well, if you are the author of this statement, then you can just, and it's like in the same paper, you can go back and improve the statement so that it now also covers the case you're actually interested in. But maybe it was written by someone else in a paper that has already been published. And so then you'll just say, well, by the proof of lemma blah and blah, which actually proves something slightly stronger, we can see that, etc. And yeah, so that's sort of extra mental, you need to spend some of your mental RAM keeping track of these discrepancies. And another thing that happens a lot is, well, okay, so if you actually were the author of the lemma or the definition that needed to be tweaked a little bit, you can do this. And now you have to keep track of, okay, which parts of my project are affected by this change? And does it break any of the proofs that were already written because I changed this lemma in chapter 1 or section 2.3 or something? Or does everything just work? And so I claim that formal maths like this theorem proving software, etc., does not decrease the raw proof complexity, but it certainly helps with taking care of these other things. And especially if you're doing proofs where there are like tons of inequalities and I don't know exactly how many epsilons and deltas independently were floating around in certain parts of the proofs, but there's like, in this proof that we were working on, there's like a doubly nested induction argument going on. So you have to doubly recursively build a whole bunch of epsilons and deltas and small k's and big k's and kappas and c's and whatnot. And they all have to satisfy bounds with respect to each other. And Lean can just help with checking that all the side conditions, like that every epsilon is positive, etc. It can just help keep track of that. And so it's a really powerful tool for that. So what is the result? Most of your personal mental RAM can be spent on understanding the big picture of the project, of the proof. And if you're working on one particular lemma, then you focus on that lemma, you zoom in, you understand the proof complexity of that lemma, you work on it. But once you're done, you can seal it off and your focus returns to the big picture. And you don't have to like spend part of your active memory on keeping track of, well, discrepancies between the statement and the proof, etc. So I think we have this idea in mathematics that once you understand stuff, you sort of compactify it and in your brain, and you have new space for new mathematics, etc. And I think that this sort of compactification is sped up when you're working with formal theorem proving software. So that's one of the advantages. And our experience from the Liquid Tensor Experiment is, well, Scholze himself wrote when he was writing about this challenge. He says, one key problem I had when I was trying to find this proof was that I was essentially unable to keep all the objects in my RAM. And I think the same problem occurs when trying to read the proof. And I can testify to that because my attempts to understand the pen and paper proof, I tried this 3 times, I think, where I just sat down and said, okay, now I need to understand how everything works, and so that I can like guide this project and understand what the next steps are. And it just failed dramatically. And in that sense, Lean was really a proof assistant. Like, this terminology is sometimes used for this software, and I think most of the time it's a bit preposterous because the software is just being really annoying and pedantic. But in this case, it really was a proof assistant because I couldn't understand the proof. I could just see 3 or 4 lines ahead. And I think there's this analogy when you're trying to read a text in a language that you don't completely understand, so that's not your mother tongue. You just try to read it in one go and you cannot make any sense of it. And then you sit down with a dictionary and you translate the first 2 lines into a language that you do understand. And once you've done that, then you see, okay, but now I can make sense of the next 2 sentences. So you translate those. And here it was very similar. I couldn't make any sense of it, but I could understand, okay, this is the statement of the next lemma, and I understand the first 2 lines of the proof. Well, let's put that into Lean. Okay, now I understand the next lines. And so this was mainly because I just didn't have to keep track of all these objects in my mind, because Lean was keeping track of the objects. So I could just focus on like the tiny bit ahead of me. And then finally, when everything was done, sort of also in my mind, the compactification happened and I understood the bigger picture. Okay, so now I want to turn to the third item, the spec-driven development. And my claim is that large projects like this benefit a lot from top-down development. And so you should write a skeleton first and fill in the details later. So why is this? Well, this outline, first of all, it helps with grasping the proof structure if you don't understand that. And like if you do a bottom-up development, you might end up developing lots of different pieces that in the end don't work well together. So if you start from the top, then you start from where you want to end and you break things into pieces. Of course, you have to, in the end, get back down to the foundations. And there's a risk that you break it into pieces that actually cannot work and cannot fit together. But I think there are ways to deal with that. And most importantly, again, the proof checker, the software gives the assurance that in the end, everything works and fits together. So you start from the top, you break things down, and at some point it should terminate. And once it terminates, you have a very high guarantee that everything is fine. So in a bit more detail, when you're creating a new definition, you write down its main desired properties. And these properties form the so-called spec, the specification. And in computer science lingo, you could also call this the API, the application programming interface. Sort of, even if you didn't know the definition, if you know these desired properties, you know how the object behaves and you can work with it. So you don't need to look under the hood. And the really important point is refactoring these specs is cheap. Refactoring a full library is not. If you've written an enormous library of formalized mathematics, it's like if you've written a paper that's 100 pages long and you need to completely overhaul it, that's a lot of work. So if you just write down the main statements and the main definitions, then you have maybe a document of 3 pages, which is really easy to overhaul. And so I think this is a big benefit. And it's also a place where we maybe deviated from what was done in the past. Because a lot of people said, well, you need to work mostly from the bottom up, because otherwise you'll be on shaky ground and you might not be able to connect the 2 ends. But we use this a lot, this strategy of working from the top down and then sort of filling in the gaps, refining where the gaps were and filling them in gradually. And so when you do this, so you make sure that everything sort of works together as well as possible, all these specs, then you can work out the details later. And that's also a place where people who don't know all the details of all the different specs and how they fit together, they can join as long as, and they can focus on one part. Like they can say, okay, I'll work on filling in this definition and proving that it actually satisfies these properties that we've written down. And so we had some pretty good experiences with this. I think the most spectacular one was that at some point we had to use Breen-Deligne resolutions. And so this is some sort of gadget in homological algebra that has really nice properties, but it's also really hard to prove that it exists. This requires stuff from homotopy theory, like stuff pretty much related to the fact that homotopy groups of spheres are finitely generated. And we were not looking forward to like checking all this homotopy theory just to get this one particular gadget in homological algebra. So we wrote down all the properties, and sort of in the beginning we were thinking, okay, we'll just have to assume the existence and make our full project dependent on that assumption. But then once we had written down the main properties that we're actually interested in, we discovered an easier object whose existence was really easy. Like we could just give a hands-on construction with very similar behavior. And actually this behavior was good enough for our purposes. And well, as I said, many key statements were written down without proofs. And after just stubbing out the definitions, and several definitions and lemmas had to be tweaked from the way they were written down on paper by Scholze, or the way we also introduced some new definitions to help us out, and some of these definitions had to be tweaked, etc. And this was just a lot easier and cheaper to do when there was not an enormous library built already. So, as I said, refactoring specs is cheap. Refactoring a full library is expensive. And after the dust settled and we sort of were happy about these specs, the work on the proofs could be distributed to a lot of team members. Sometimes we actually did need to refactor a large proof or some large libraries, and that was pretty painful. So at some point we had to overhaul the homological algebra library in Lean, and that was just 2 weeks of painful work. But once it was done, it was worth the effort because things worked a lot easier. But this, I think, one way to summarize this is plan ahead carefully, and that will pay off a lot. And working top down is a good way to see how you should plan things out. Okay, so now I want to come to the last point, which is this confidence, trust, and evidence. And I think, right, we've written this enormous, like 90,000 lines of Lean code that claims to check a recent theorem by Scholze. But how do you actually believe that what we did matches what Scholze has in mind? So Pollack wrote a paper about this in 1997, How to Believe a Machine Check Proof. And well, all the way down at the bottom, you have to trust the hardware. You have to trust that like CPUs are not just doing something crazy. And like if you're really paranoid, you have to trust that some cosmic background radiation didn't flip some bits while you were checking the proof. You have to trust the software. So is the proof checker actually checking the proof, or is it buggy and just saying, yes, everything looks fine, whereas actually it just messed up? And you have to trust the statement that is being checked, because we need to check that some X groups of condensed abelian groups are 0. Well, maybe we just defined X groups to be 0 in the first place, and then the proof would be extremely simple. So you need to check that the definitions that show up in our statement are correct. Well, the first 2 issues are more or less solved. I mean, you can trust the hardware by, so these days, a lot of hardware, like processors, are also following formally verified specs. and being implemented that way. You can battle the cosmic background radiation issue by just checking the proof 100 times, and then the probability that cosmic background radiation is messing with you 100 times in a row is like vanishingly small. You can trust the software because nowadays proof checkers have an extremely small kernel that does all the critical stuff, and then so the correctness of the proof checking depends on like 3,000 lines of code that has been very carefully written and very carefully checked by several really competent computer scientists. So we'll assume that we trust the hardware and the software and mostly focus on like how can we convince ourselves that we got the formal statement right. In other words, how can a casual observer gain confidence, gain peace of mind that the following three align? You have your mental model of mathematics. You have the pen and paper representation of mathematics, namely what Scholze wrote down in his challenge blog post or in his lecture notes on analytic geometry and liquid mathematics. And then there's this formally verified representation of mathematics, namely the lean code that we wrote. And so how can you check that the mental model that you have matches this this pen and paper mathematics that Scholze wrote and the lean code that we wrote? Well, if the statement were easy, for example, Fermat's theorem, which only depends on like multiplication and addition and powers of natural numbers, then this is sort of easy because you can easily check all the definitions involved. Like you need to check that the natural numbers are what you think they are, and that addition and multiplication, etc., are what you think they are. Maybe you want to check the notation to see if this plus symbol actually refers to the addition of natural numbers instead of some wacky other function that just, I don't know, returns something that, like if addition would always return 37, then the two sides of Fermat's equation will never match. So maybe you need to check notation. And if you're like really, really paranoid, you might want to check that the people writing the formally verified code didn't mess with like invisible Unicode characters that did something completely unexpected. But anyway, this is all not so hard to do. Well, the main statement in the Liquid Tensor Experiment relies on more than 1,000 definitions, like recursively. In the main statement, you see real numbers, profinite sets, p-Banach spaces, condensed abelian groups, and these ext functors. And if you start looking under the hood of these definitions, you see that they are defined in terms of other definitions. And if you, like, this is one of the nice things that we could do once we were done, we could just ask Lean, okay, how many definitions have been used in this entire project? And Lean spit back, well, several thousand. Okay, so there you go. If you want to check all the definitions, you have to check more than 1,000 definitions. It uses pretty complicated notation to hide all sorts of functions and parameters that are not written down on paper and that are usually irrelevant. So you have to make sure that this notation isn't doing something stupid. And to make things worse, we actually use some 0-width Unicode characters to transparently trigger some automation that helps keeping the statement readable. So yeah, why didn't we mess up, or why didn't we do something evil? And our solution to this is, did something, can you all see my screen okay?
Yeah, it did something weird for a second, but now it's back.
Okay, good. So I think the best method we have for this, like, of course, you don't want to spend 1 year to convince yourselves that the Lean project, that this Lean code is saying what you think it says. So our answer to this is to use abductive reasoning, also known as like, does it pass the duck test? If it looks like a duck and it swims like a duck and it quacks like a duck, then it probably is a duck. So what we did was we created a folder, the examples folder with 5 files. And each of these files focus on one object that occurs in the main statement. And it's really important these files are short, well documented, and readable, because Lean code usually is very readable, especially like theorem statements and definitions. But like the gory guts of the proof, they're very hard to read if you don't know Lean. But these files should be readable with very little Lean experience. And then these files should exhibit like the standard behavior, the spec of the object, in the sense that we were talking about earlier. So here's an example of that. One of the things that shows up in the definition or in the main statement are profinite sets. So a profinite set is a topological space that is compact, Hausdorff, and totally disconnected. And you can build a category of profinite sets, and a morphism. Oh, sorry, I made a typo. A morphism of profinite sets is a continuous function. So you just consider them as topological spaces and continuous functions between them. And then a condensed abelian group is a pro-étale sheaf on this category of profinite sets. So it's a contravariant functor from profinite sets to abelian groups that satisfies a certain sheaf condition. I'll not go into the exact details, but now we can like go to this file. So we are in this examples folder. Let me increase the font size a bit, maybe. Something like this. Okay, so as you can see, we're in this examples folder in the file profinite.lean. And we just import the full challenge so that we have exactly the same definitions and notations, etc. And so then you can see, okay, if you have two topological spaces, then this thing C x comma y consists of all continuous functions. For example, it gives you, if you have one of those, an f that lives in C x comma y, then it gives you a function from x to y. And in fact, this function is continuous. And on the other hand, if you have a function that is continuous, then you can create an element of C x comma y by just bundling up together this function together with the proof that it's continuous. So that's good. And so now we get to this definition of profinite sets. Well, actually not the definition. The definition was already there, but now we can check that it like swims like a profinite space and it quacks like a profinite space, etc. Because if you have one of these X that lives in the category profinite, then it is a topological space. It is compact. It is T2, in other words, Hausdorff, and it is totally disconnected. And vice versa, if you have a gadget X that is a topological space and satisfies these other three conditions, then you can build an object of the category profinite. And now here you can see if you have a morphism between two of these profinite sets. Well, I should say the type, okay, the type of all morphisms, the set of all morphisms between two profinite sets is exactly this set of continuous functions. Well, and then you can see, okay, there is this Grothendieck topology on the category of profinite sets, which is the so-called pro-étale topology. And here's a long example explaining exactly that if you have a contravariant functor from profinite sets to abelian groups, then it is a sheaf for this pro-étale topology, if and only if some complicated condition holds, which you can check matches exactly what is written down on paper in the lecture notes on condensed mathematics. So it has to satisfy a sheaf condition with respect to some jointly surjective families. And finally, so if the category of condensed abelian groups is exactly the category of sheaves of abelian groups with respect to the pro-étale topology, etc. So this file is like reasonably short. There are lots of comments written, and yeah, I claim it should be pretty readable for someone who has never even seen Lean before. And so what we hope is that using this method, people can easily get peace of mind that what we've been doing in Lean matches what is done on paper without having to check the 90,000 lines of code that we've written. Right, so my claim has been that formal mathematics helps with breaking the one-mind barrier in the sense that it helps a large group of minds, people collaborate together. It reduces cognitive load so that you can do more with the mental RAM that you've got in your mind. It helps with this spec-driven development. It makes that easier to carry out, which again feeds back into making large collaborations work. And it helps the larger mathematical community gaining peace of mind that this fundamental theorem that Scholze has been proving is actually true without needing to understand all the gory details of the proof. Thanks for your attention.
Thanks, that was great. Yeah, so if anyone has any questions, you can put your hands up or just speak up. Oh, Valeria might have one in the chat. Okay, can you see the chat, Johan? Here's a first question for you.
Let's see.
Valeria asked, basically asking, I was wondering what a liquid vector space is. I am also wondering what a liquid vector space is.
I see, okay.
To say or not, but yeah.
Yeah, so, okay, I can sort of try to say something about that. I considered putting some part of that into the talk, but I was afraid that that would actually make the talk way too long, but I see that I actually had some time left. So maybe I should have done that. Anyway, so a liquid vector space, the idea is that if you, let's say, okay, so it's sort of in the context of functional analysis. So let's say you have like L1 space, the space of L1 sequences and the space of L2 sequences, and there's a natural map. So L1 sequences are dense in L2 sequences. And so now if you take the quotient, you get a pretty horrible space. It's sort of discrete because like you quotiented out a dense subspace and doesn't really capture anything meaningful. And if you try to complete it, you just get 0 because it would be the same as like taking the quotient by the completion. So complete topological vector spaces do not form a nice abelian category with good properties because like the inclusion from L1 into L2, it has trivial kernel, and in the category of complete topological vector spaces, it also has a trivial co-kernel, but it's certainly not an isomorphism. So what liquid vector spaces try to do is to use this whole framework of like sheaves on profinite sets to build really nice abelian categories where complete topological vector spaces naturally sit inside them. And the idea is that, okay, if you take this quotient of L2 modulo L1, then, and you record all the way that you take this as a quotient of sheaves, then maybe if you evaluate the sheaf on the 1-point set, you get 0. But if you look at you take sections on other profinite sets, then you get larger quotients and something meaningful is still happening. And well, then Scholze and Clausen show that if you know this main theorem about liquid vector spaces, which is saying that a lot of X groups vanish, which means that the category of liquid vector spaces is a full subcategory of the category of condensed real vector spaces, that is stable under all limits, under all co-limits, and under extensions. So basically, whenever you're inside this category of liquid vector spaces, it's really hard to get out of it. So it's a really nice subcategory where the objects behave as if they are complete. So if you just have a random condensed R module, that would be just a random topological vector space. But these liquid vector spaces behave as if they are complete. Okay, and it's a really nice category. And then you can generalize this so that you don't only take modules over R, but you can take modules over C or any C algebra, basically, let's say finite dimensional or something. And actually you can do this also in a more geometric setting where you're considering like liquid sheaves over a geometric base space. And then they started to apply this to classical theorems in analytic geometry, like Serre duality or finiteness of coherent cohomology, etc. And they found really easy algebraic proofs of these statements that used to have extremely complicated proofs. But everything depended on this main theorem, where it seems like all the functional analysis and all the bounding inequalities, etc., everything is bundled up into this main theorem, which you can use without understanding the proof. So it's a really nice black box, but the proof better be correct. And so that's why Scholze challenged us to do this. Okay, I don't know if that answers your question, but it does.
It does. That's what I wanted to hear.
Yeah, okay, cool.
I wanted to hear some sort of general idea of why they're doing that and how. And it's kind of, I mean, I like the story that you told us, because it has lots of category theory on it, right? It's about kind of this subcategory that has all the good properties. That's great.
Yeah.
Evan, can I have a more specific?
Yeah, we've got plenty of time, so please go ahead.
Good. So the other question then, Johan, is about, I mean, the way you gave the talk, it does not look like it has terribly much to do with lean. You know, it could have done this way of specifying things and breaking them down and stuff like that could have been done not only in another theorem prover, but even perhaps by mathematicians that had this ability to connect things, right? To have this, that had this computer-assisted way of saying, well, I depend on this and this and this lemmas, and each one of them depends on this and this concept, and they have been connected this and this ways. So I think the question is that true? Kind of, could we actually even do it? You know, the way you showed the blueprint thing, kind of connecting the two different graphs, it looked like, you know, so long as I had been able to construct the graphs, whether I mapped that graph into a lean proof or not, you know, or in a Hall, Isabelle Hall proof or not, or even, you know, just to a piece of text, would be this, you know, would work.
Yeah, so I think yes and no. So, I mean, one of the goals, one of the things we're working on now is, now that we've sort of digested this proof into lean, we want to find ways to conceptualize it in a better way, so that we can write a pen and paper proof that can just be checked the ordinary way and understood the ordinary way by a human mathematician, without needing to rely on computers or anything. But I mean, for me, like, I spent like day and night trying to understand this proof. And okay, I mean, I'm just a pretty average mathematician, I guess. And I just really couldn't understand what was going on. And I really needed this translation into lean, line by line by line, before finally things started to click. And so I think in principle, it could have been done by human mathematicians, but I think there would, at least the way the proof is written down now, there would always be this sort of lingering feeling that Scholze also had, like, did I actually mess up one of the inequalities? Did I make a mistake, flip a sign somewhere without being careful? There are so many inequalities, and everything is like influencing each other in pretty unintuitive ways, because the proof applies several strategies that Well, Scholze asked the math overflow question, like, is this strategy, has this been used before? And he basically didn't really get a satisfactory answer. So it's applying new strategies that people didn't really have any intuition for, and I think maybe they still don't have, apart from the people who have been working on the lean proof. But even then, like, we had a discussion about this 2 weeks ago, and together with Scholze, and we said, well, we basically still don't really have a good intuition for why the proof works. We see it, like lean says it does. We understand line by line how the proof works, but we don't really have a good global intuition yet. So that's some of the, we have some ideas how we could maybe improve on that, but nothing definite yet. And so it builds, right? You can check one lemma by hand. You can check the second and the third lemma by hand. And then you start putting the pieces together. You saw this one graph, it was really large. And at some point you start losing the faith that what you're doing is 100% correct, because there are like so many pieces of the puzzle. If you don't have something that like has a completely rigorous way to check that everything fits together, at some point you start thinking, okay, somewhere probably something was messed up. And I mean, the proof that Scholze initially wrote, there were things messed up. At some point he had to like fix a statement, and he was really worried. And I think he stayed up late for a night, and then the next day he popped up back in the chat room and he said, yeah, okay, I think I fixed it. But he really was worried. And several other times, like some inequalities had to be tweaked a bit, and constants didn't have the correct value, etc. So we made everything work, but I don't think I would have been able to do that just with pen and paper.
Right. Thank you. I mean, it does make lots of sense to me. And presumably for this proof, definitely you needed everything. But I was just thinking that, you can abstract over this idea and say that for lots of other proofs, just this computational, because you also need the computer to do the business of building up the graphs and building up the connecting all the definitions, otherwise you might forget one and things like that. And that is not particularly, I don't know how much
no. I mean, actually, like you probably know the Stacks project, this massive online reference work in algebraic geometry. For a long time, they also had these sort of graphs. So whenever you had like a \ref in the LaTeX source, it would generate an edge in the graph. So you could see how a proof of a certain theorem depended on all the other lemmas in the preceding chapters. The downside of those graphs, well, there are two downsides. One, they don't exist anymore because the new version of the Stacks project backend doesn't have this feature. And the second downside is, like in a usual mathematical document, you don't link back to definitions when you use them. So you only link back to theorems and lemmas. And so the graph was not complete in that sense. There were only nodes for lemmas and theorems and edges when you use them in proofs, but the definitions were missing from the graphs. But so, I mean, this idea has certainly been tried out before. And I think from a like meta mathematical point of view, a mathematical knowledge management point of view, there's a lot of interesting stuff there. And yeah, certainly.
Many thanks.
So I wanted to ask a question. Oh, did someone else have it? Did I hear another one?
Yes, I'd like to ask
Go ahead, yeah.
Meta questions about a single question. So the single question is just something that came to mind while you were describing profinite sets and sheaves on the dual category. Oh, dual category of profinite sets, that's Boolean algebras. And the way my RAM works, I would probably be thinking about the Boolean algebras rather than the profinite sets. So the first meta question is, does it even make sense to ask whether the formalized proof, quote, thinks, unquote, in terms of profinite sets or in terms of Boolean algebras? Is it ever useful to move over to Boolean algebras, or does Lean just not see, who cares? I'm a computer. I just work with what's there. So that's the first meta question. And the second is, if the first one makes sense, would there be any way to get the answer? Does anybody actually know how Lean was using these concepts? Or is that sort of hidden away, probably best not asked about?
Yeah, interesting question. So, I mean, Lean certainly is really just a computer. And I think one of the most famous quotes that is used all the time in the Lean chat room is Lean doesn't do magic. So in particular, we didn't really use any artificial intelligence or anything. Lean is just like the way you do formal proofs in logic, right? You have statements and you just have rules. If this is true, if this is true, if this is true, then that is true. Okay. And that's sort of what you apply all the time. And then you use tiny little computer programs that start doing that for you, because otherwise it wouldn't scale. Like, you cannot do such a large proof if you have to do everything like axiomatically by hand. So you start writing little computer programs that generate these formal proofs for you so that you can work on a higher level. But in the end, Lean just works with whatever it gets. So probably Lean knows that the opposite category of profinite sets is equivalent to Boolean algebras. I'm pretty sure it does. But like, we didn't use that equivalence in this project. And so I mean, to the extent that you can say that Lean thinks, which probably, like, maybe the answer to your question is it doesn't make sense. But to the extent that Lean thinks about profinite sets, it thinks about them in the way I presented on this slide. And then, so from a mathematical point of view, the reason I think people would want to work with profinite sets instead of Boolean algebras is that this functor becomes contravariant. And so it's a sheaf instead of, I guess, a cosheaf. And there's like a whole library of knowledge about sheaves and topos theory, etc., etc., etc. But I mean, that maybe diverges from your question. So yeah, I think the answer is probably it doesn't really make sense to ask what Lean thinks. And like, if you prod Lean by asking, okay, which definitions were used, then it will just say, well, I used the definition of profinite sets. And if you ask, okay, can you tell me what the definition of a profinite set is? It will say, well, it's a topological space that is compact Hausdorff totally disconnected.
And it would not make sense to ask, did Lean find it useful to take advantage of its knowledge of what the dual is? Because nobody prompted it to use that knowledge. It has the knowledge. If you don't tell it to use it, it won't.
I mean, so here you get into this field of research that is under extremely active, that's really active right now. Like, can you start using artificial intelligence to start finding proofs for you? And given that Lean now has a pretty vast knowledge base, like, we're covering almost an entire undergraduate curriculum in pure mathematics, I would say, and a lot of stuff that goes beyond that, say all this topos theory, homological algebra, etc. So you could try to have like artificial intelligence generate some proofs for you, and then they might find this kind of knowledge extremely useful. But we didn't really do that. And so, I mean, we made some of these programs that we used did a little bit of proof search, but from the way I understand how they work, I don't think it's likely that they would start looking for equivalences of categories. They're much lower level, I think. Yeah.
Okay, thank you. And I have to apologize. I have an appointment at this very moment, 2:00. So I'm going to disappear.
Yeah. Thanks for your question.
Thank you very much. That was a very interesting talk.
Yeah, so thanks. Let's thank the speaker.